So, welcome to the talk. Let's start to do some hardware hacking. The title is How to Hack Any Microcontroller with a Raspberry Pi Pico. Let's jump right start. So a little bit about who am I, about me. Name is Tongren Chen, also known as Chen. I'm a cybersecurity engineer and researcher working at a consulting firm in Tokyo. And you can contact me by the email address and also find me on LinkedIn. So yes, let's jump into the talk. Agenda, object of the talk, then some background, the new approach, proof of concept, part 1, part 2, conclusion, and some bonus slides. So first, the object of the talk. We propose an easier method to hack any microcontroller, which is, the category of the hacking is precise fault injection. The hack should be target independent, and the attack should be precise. And this attack should, does not require full-fledged driver. And the attack should be also fully customizable. So let's talk something about the background first. Background about the fault injection. What is fault injection? The precise fault injection. So what is it? Fault injection is a hardware attack against integrated circuits. How does it work? Well, it injects electronic errors to the circuit and then abuse the undefined behaviors it generated, which could include the corruption of data or a few instructions are skipped. There are various techniques of doing this fault injection. The one we are talking about will be voltage glitching. There are other techniques, but our focus is first precise attack, and this variation, but other techniques are also compatible. So how to do it exactly? Well, the approach is to briefly short the integrated circuits to the ground. Why is it effective? Because by doing this, it causes ringing in the circuit and the setup time violation, according to research. So we could explain a little bit about what is setup time. Setup time is a time we need to wait until all components in an integrated circuits involved in an operation to be ready. That is to say, electronically, components needs time to charge up. Then we also need to make sure every component is ready at the start of any operations. Otherwise, errors. Garbage in, garbage out, you have errors. About other relevant works is the crowbar voltage glitching method, which is also the chip whispers method introduced by Lin. It basically uses a set of glitch parameters, including glitch offset, width, steps, etc., to achieve fine control on the timing. And our code uses similar parameters. Next, about some main steps to perform a precise voltage glitching. Well, those usually includes the following. First, identifying where to glitch. And it means to identify the vulnerable moment at which we would like to insert the glitch. Then the second is identify and capture a digital trigger. A trigger is a signal or an event that can be automatically recognized by our hardware, so that at that moment when we detect the event, a glitch can be automatically inserted. And also we would need a stop signal as well. The stop signal function it is also an event, but once we detected it, the attack has to be stopped immediately, because we have the attack glitch has succeeded. We have entered the state that we want, and we have to send the exploit. And what is an exploit? Let's come to the final steps, is by issuing commands that a chip can understand. Namely, whatever we're interested in, for example, dumping the firmware or something about that. So let's look at some examples. First thing, it's in research in tutorial. Usually we encounter a noun that is called a perfect trigger. They say we assume a perfect trigger. What is a perfect trigger? Well, a perfect trigger is actually an analog signal, not a digital one, an analog signal, which can be generated by simply, to flip a GPIO pin on and off. Then we can use make it wrap into a function and call the function just before the critical logic. So that's because in those scenarios, the glitch, how the glitch itself affects the critical logic is our point of interest. It's what we want to know. So this is perfect fine. We got by this we can got the perfect timing. However, in real world, things got a little bit more complex. So it is not that straightforward to acquire a trigger in the real world. So how did people do it? There are two examples shown here. One is PS4 and PS Vita hacks. Basically, whatever the target device is, remember that our first goal is to pinpoint the vulnerable moment, which means understand what the chip is doing and when it is doing it. But how do you know it? How to know it? How do you ever know? One method is to observe what a chip says while it's doing a task. Well, interestingly enough, chip has to say something because it's a chip's sole purpose to interact with the actual world. Also, considering the maintenance or reprogramming purpose, a chip usually have some ports open for the interaction. So come back to the PS4 hack. The PS4 hack used listen to the tool 0, it's a debugger line, communication line, which we will use later in our attack as well. The PS Vita hack, on the other hand, will listen to a communication line to the eMMC, which is a external storage chip. So we know where to listen to. We listen to some communication happen on some lines. Then talk about that, we have to understand the communication, which naturally is what a driver do. So that's why people implement a driver. So yes, and also they follow the same 4 steps, 4 major steps in the process, which is it's not the most easiest thing to do. And also the driver source is in the link. You can click and you will see it. But I mean, they're not the simplest thing to implement either. So can we make things simpler? Well, let's take a look. So why need a driver? Well, we already established that the sole reason we need a driver is to talk to a chip and make sense of some analog signal sent back by the chip. To perform an attack, which means basically it's just like 2 directions, right? We need to send something that chip understand, and we need to some extent, understand what is chip talking back to us. That's about it. And next step. So what exactly is the driver doing? We'll explain the detail of how it is done later in the slide, but basically, there are 3 steps. In the first 2 steps are quite straightforward and simple. Step 1 involves it's basically convert voltage to a bit. That is like acquire voltage reading at this very specific timing, then pass it to a bit. If it's a 0 volt, it's a 0. If it's high voltage, 3 volts or something, it's a 1, something like that. The second step is to parse bits to a byte. So bits can include a bunch of other bit start, stop, checksum, etc. And it also have a order SB, MSB, right? We pass it to the byte. But those 2 steps are usually quite simple logic, and they are commonly should be documented publicly in most cases. But there's also a third step, which is to bytes to a frame. What is a frame? So if we use an analogy, Example, well, can be that a bit is like more like a Japanese goju character, while a frame can be a sentence. The difference is a sentence has lexical structure. It has more grammar. It is far more complex than like a byte. So the step 3 is not easy to implement at all. It involves and those grammars may not be like publicly documented. So yeah, it is hard to implement due to a few factors, namely lack of a document, difficult to debug. Well, because we have no working drivers, how are we supposed to debug a driver before we even have a working one? So naturally, it's become well. It's hard to validate assumptions, and it needs some reverse engineering to implement sometimes. And also, implementation has to be done like one logic at a time. Means the capture is sequential, so you only have a whole capture. You don't know what is optional and what part is more critical, so you have to basically do it sequentially, which is like involves a lot of work that is may not be fully necessary. Now, what about the new approach and like any challenge about that? Let's talk about our approach. The new approach, yeah, the goal is to talk and understand about the chip. So, and the difficulty we established about that's the most difficult part is step 3. How about record and replay something? What do you mean? So by record and replay, we means well. The record part is quite easy. It's easier to do because it has a few merits. I mean, the traffic are easily obtainable by just connecting a new chip, set up a new chip, and a debugger, or like a test board or something, and a debugger. They're readily available for commercial chips. But the challenge there are two challenges majorly. One is that traffic can be bidirectional for one-wire protocol. Like they need to be isolated. It's like two person talking on the end of a telephone across the same telephone line. However, their voice are identical. They have the same voice. How are we supposed to? And we do not understand their language. Then how are we supposed to to make sense of who is talking? And second is how to record and replay the analog signal. Basically, these two problems, and let's take a look at our solution. Solution 1 isolates the bidirectional one-wire communication. So first, let's take a look at some like non-protocol. Non-protocol means SWD, which just look at the picture. All right, so we can make some observations. That is, by the way, this capture is a capture of SWD traffic of the ramen board, which was also present in Code Blue last year. We will introduce later. But a key point is there are anomalies, means spikes and voltage drops, noise but they are repeated patterns. And interesting enough, just by looking at those anomalies, we can actually identify the direction of those the traffic. However, those are too tiny, and also unfortunately, it's hardware dependent. Means once we move to the breadboard, those spikes does not exist anymore. So they're not enough. We would like something more. But nonetheless, this is a hint that a hardware solution may exist. Insert a side note about what happens behind a GPIO pin. Means like the communication line, they have a pin, but what happens behind the pin, right? How is it implemented? So the key point is there may exist a few components behind a GPIO pin. Let's think it as a black box that has some parasitic attributes. And also, maybe a GPIO pin can pull the voltage up or down, up to 3.3 volt or down to 0 volt, something like that. And also, they may exist in hysteresis switch, which is the red rectangle, which means it's a switch that turns on when and only when a voltage threshold is met. So the jump back to the solution. The solution circuit is fairly simple actually. So just look at the circuit, right? So the first thing first, the ENV UCC pull-up registers the ECU debugger. Those things, those connections, we do not need to worry about because they are actually documented. Like it's according to the recommended connection of my official document. They are part of the recommendation. The only modification we did is that just add a tiny resistor R1 to the communication line and probe on both its sides. So yeah, what's the result? Result will look like we got something like this. Okay, there's something going on. What is happening? If we do some analysis, we can see that first we look at all digital 0. Interestingly, when a sender is sending digital 0, it becomes a ground. Because you have to send a 0 volt, it becomes a ground. So if we look at the voltage at the two probes, we can make a first important observation is that the probe on the sender side always have a lower voltage. This intuitively makes sense because when you are probing around the ground, you are supposed to get a 0 volt at the ground. Also, thanks to ENV BCC, usually in this scenario, the delta V means the other probe, which is not 0, should have a higher voltage, higher enough voltage. So yes, this is the other direction, right? The left-hand side, the chip side, becomes the ground. In this scenario, practically in this scenario, the important thing is maybe, like in some cases, the delta V, the voltage difference between the two probes are too tiny to make sense. Although the sender size probe definitely has a lower voltage, so the rule 1 holds. But let's take a deeper look at the example. Maybe it's easier to understand. So example capture is here. So first, look at the purple rectangle. Well, the delta V is different enough. So lower voltage is lower side is sender. So the purple one, which is that the debugger? Oh, yeah, it's a debugger side. Debugger is a sender. We know we can identify that. And about the left-hand side, the assign rectangle, the delta V, the voltage difference is too tiny, maybe prone to error. But fortunately, there are only two directions, so we already know one. So this is the other direction. So congratulations, we separate the isolated direction. Solution 2 is the second problem is to record and replay analog signal. So remember the first two steps we have to take. The first step, measuring the voltage. Actually, it's done using an analog digital converter in the electronic world, ATC, at a specific timing. Then pass the bit according to certain rules. Well, as for the step 1, we do not have to re-implement. Well, it's you can do it with a logical analyzer. It will just capture all the data very fast, 5 million times a second, and we have the raw data, right? Then we just process the raw data to a byte. We can take a look at the example. The example is that, well, we have many data. Actually, we have plot them in series. We have a graph. Then, of course, as I mentioned, the two steps are documented. They will tell you how the official documents usually tell you how to pass a byte, right? So we start counting at once the voltage drop to the 0, then count half of the bit length, and there's a start bit and 8 data bits. Then we got a byte. Then also then is the end bit 1 or 2 bits always high. Essentially what we managed to do here is that. So on the left-hand side, it's a raw capture from a logical analyzer, which is timestamp, voltage, voltage, voltage. And in a red rectangle in the middle column, we can see voltage drop from 3 0.3 to around point like 6 or something, which is a falling edge. So by using this logic, we can like convert the raw data to actual bytes with direction with timestamps. So yeah, part 2, solution 2 solved. So POC, actually how we like use the methodology. So yeah, let's use it. And the target is the RL78 chip. The goal is to the four steps plus that we have to prepare the victim chip to the correct state so that we can insert a glitch. So yeah, the first step, capture good communication. Good communication means just set up doing the probing circuit on a new chip, a target board, or like and a debugger, right? And we dump the memory, use the default software, default anything, everything to capture the communication. We got the traffic, perfect. Step 2, to identify the useful chunks for us. Well, I mean, replay it. Just replay. Since we already can replay the traffic, we just replay the debugger's part, right? Replay from the start to the end. Does it work? Wow, it worked perfectly. Yes. Okay, so now, since what we are interested in the data extraction part, right? So replay near where only the data is extracted. Well, it did not work. So where the part is going wrong? Just repeat like you replay from earlier timing until it worked, right? So by this method, we can like soon identify the critical chunks and also the optional chunks. So yeah, this is an example of the critical chunk. There's a handshake chunk, which is also documented, but also it's in the like at the start of the traffic of every communication. And also here is to identify where to glitch. So remember our interest, since our interest is the firmware, so it's just the quality of time, quality of life improvement is that we can insert some magical bytes before the start of the firmware. Then you can search the byte sequence and to identify where the data is located in the dump. So yeah. Then where to glitch? Yes, we have encountered this part that basically, if we replay after this section, everything fails. So okay, this must contain an important logic, and after inspection, well, it's we know this is a critical chunk, and when we inspect and see, we see security ID and checksum sent by debugger, and there's a response from the chip. Remember that we know which who is talking, right? So we sending something, then a response came back. So almost at this step, we got everything we need. The digital trigger, well, it's just since we are sending before the processing started, so we can just not send all bytes and send the last, like just pause before sending all bytes, and then send the last 1 or 2 bytes. This event can be used as a digital trigger. Now, what about stop signal, like the success signal? Well, just try different scenarios on our new chip. Just do a success, unlock, a fail, unlock, not locked, like capture the traffic and compare. We got this success signal, this hex string. Then yeah, what about the last part is the command sequence to dump the data. Actually, it's like kind of no-brainer. You just replay everything before the data it work. And yes, let's take a look at how to implement it in hardware, the actual implementation in hardware. So in this section, the goal is to implement the attack, and details on the hardware. Full source code is on my GitHub. The schematics is as follows. If we look at so left-hand side is the schematics, right-hand side is the breadboard view. Nothing crazy. It's just a Pico with 2 on-off switch. If we look at the yellow line is the probing circuit we already talked about. The red and black is like 2 probes, and there's our resistor. And also we have orchard this line which is connected to the 2.0 as well, but on the chip side, right? It is listening, actively listening to the what chip is talking back to us all the time. Also, there's a reset line that we have to set to high and low according to the document. And the key part is that the two switch, it's just one switch, glitch control switch. When activated, it shorts the REGC pin, which connect to the core of the IC of the chip to the ground. Well, when flipped on, it will short the chip. Basically, that's it. And there's a power chip on-off switch for the chip, because we need to keep this. We cannot turn off the power of the Pico ourselves, because we will need to keep the state. Remember the crowbar-like glitch parameters in the Raspberry Pi Pico. So yeah, a state need to be kept. So we have to do reset on the chip only. So yeah, the basically component a Pico and the two high-speed switch NPN transistors. There can be like a BJT or MOSFET, as the type is here. And any ADC device, like a logical analyzer or maybe a Pico, you can customize it to ADC as well. About Pico, something interesting about this device is that first, it is a microcontroller. Different from the Raspberry Pi, right? A microcontroller, it runs one program. And it has direct hardware accessing GPIO pin with one PIO ASIM instruction, which means also it is super precise. Means that in the document it says all PIO instructions execute in one clock cycle. Yeah, so we can look at examples later. Also, it has a very small instruction set, which include a total of 9 instructions. Well, it has 2 cores, surprisingly, and it's affordable, like a 10 times, I don't know, 1/10 price of a Raspberry Pi. Also, there's like the internal include like a 2 or 3 PIO block, which one basically they have a full state machine. Everything is communicated with using FIFO pipes, and each state machine can run assembly code in parallel at the same time. Oh, that's something about it. And about more detail, please look at the great video by Stack Smashing. It's explained a lot better than me explaining here. A proof of concept, look at the glitch. This is a spike. Just look at the graph from the oscilloscope. It's a spike generated, smallest, tiniest spike generated by Pico. Just flip the pin on and off. Well, it took 2 instructions, which means 2 clocks, which is around 16 nanoseconds plus. Like, I don't know, it's about that time. And yeah, we use this spike to control NPN transistor, so to create the glitch. The glitch we already talked about, we want to short the IC briefly to the ground, right? But if we involve the transistor and other components, the components themselves has their own electronic attributes. They will have delays and other noise and things. So around 150 nanoseconds, the glitch looks better. And also, if at 400 nanoseconds, it looks better. But the MOSFET side has more like oscillation or some like spikes, right? It's the gate surge or something, I don't know. Well, this noise can be reduced by some flyback diode and other method, but it's beyond the scope of this topic, and if you want to do it. But for me, I just use like a BJT transistor. So yeah, the glitch logic, it's just flip things on and off, right? You short things to the ground, and very quickly, very precisely. Basically, you set things up, you glitch at the digital trigger, then check the stop signal. If a success, then we replay the data extraction commands, stops the execution. If fails, reboots the target chip, done. So what actually the attack looks like? It looks like something like this in the oscilloscope. So Hex FF is the checksum byte. Checksum byte, and then we insert like the glitch over and over again until we get the success signal. Then on the right hand side is a zoomed up view, which is like 800 nanosecond of the actual glitch waveform on the purple waveform. So in logical analyzer, we can see similar things, but because you will notice the waveform is a little bit different in logical analysis. It's just because logical analyzer is not fast enough to capture the actual shape of the full shape of the glitch. You can do the calculation, but yeah, actually in logic analyzer, you can see attacks like this: the attack or the glitch fails, reset, and I mean one success, and we got this firmware dumped. This repeated in different configurations, and the other success, right? Another success and success with all the like protection bytes flipped on or something. But yeah, that's some caveat, but basically it is like this. And something about some tricky we encountered is that how to capture. So we remember we have to capture it, not only identify but also capture it to a stop signal. The hard part is it's like you have to monitor the traffic all the time, and it's basically the attack we have two tasks. One task is to send things. One is to receive. The send part includes all setups and like the glitch, everything that we send. Receive part, well, it includes monitoring the response from the chip. Then both tasks involves some level of like high level logic, which is hard to implement in the simple assembly. So both tasks runs continuously in parallel. Therefore, it's convenient to run them in different cores. That's how we implement the things. It's like, thank you, 2 cores. Conclusion. For this glitching attack, the conclusion is as follows. We propose that improves the precise voltage glitching technique, which does not need a full-fledged driver, by achieve same effect by like replaying the traffic. And this method is vendor chip independent, and it's a minimized effort because we do not need to implement a driver, and also it's accessible from the start. Means it's debuggable. Wow! And if you want to implement a driver, it can help you identify critical communication trunks and everything else. It's useful and powerful. The POC, yes, R78, we dumped the firmware with on the document command. It's included schematic and component, and the code is in my GitHub. Conclusion, other notes is that to increase the success rate, one thing we can do is to slightly under voltage the chip. There's a research study about that. But then to handle high-speed device, it's good to like negotiate. We can just negotiate at a lower speed. And also, there exists other vulnerable parts on this chip, namely the program commander, according to other researchers. The bonus part, the boot sequence and some magic. So how an OCD, like how is a chip booted into the OCD mode or something? So let's look at the boot sequence. So first, it is a part of the hardware specification that the program counter on the program counter register, or like in x86 equivalent is something like EIP or RIP. This register points to the first byte of ROM. First byte of the 2 bytes of the firmware, which is this is like explicitly written in their hardware document. Then it will jump to this hex D0 address, which contains another branching instruction, which jumps to another place, which is the monitor 2 area, another area. But then in which it contains another jump instruction, which will lead us to the actual OCD on-chip debugger code. And this section of code is inserted like on OCD Connect by the debugger itself. So it was original or 0 or something. Then after the code execution, redirect back to our user firmware, the start of the firmware. This is how a chip this chip enable its debugger mode or something, or at least how it's debugged. Then knowing this, what things can we do is that we can insert this short assembly at the start of our firmware. Actually, by inserting this, we can choose to disable the OCD mode, right? But the OCD mode, when using this firmware, it will be default on. It will be forced on. So if we look at the right-hand side, this code, this firmware, it does not contain a critical like on-chip debugger section, which it's supposed to have. But I mean, and also yes, we have to rewrite one magical byte and this checksum to do this. But yes, use this firmware, the OCD will just work. The other thing we can do is that. What about this? Yes, this is like basically wipe everything, enable all protection. But once we flash with the magical firmware, what happens is that we got OCD connection or something. Like it will fail at some point when we are trying to write. If we still remember in the sequence, we're trying to write the OCD code into some region. If that region is like protected or something, it will fail. But until that point, yes, it talks back. If I'm not mistaken, like I think in the correct state, it is not supposed to respond with anything. And maybe it's doubtful, but yes, it does not necessarily mean anything. But these two bonus could be a possible attack path if we attack from the program vulnerability program path. So we can write some part of the code and redirect execution that way. That is about this. Especially thank is a Ramen project created by Camille, presented last year called Blue Car Hacking Village. It's an intuitive tool that bridges the gap between software and hardware and introduced me to the world of hardware hacking. So for newcomers to the hardware hacking world, one of the great thing that helps a lot is something that just work, and this is a physical thing that you can touch and just work. And yeah. Thank you very much. And this is the bibliography, and we can have time for some Q&A.